In section 6.3, we're looking at integrals of a form of some trigonometric functions. There's three types in this section. The first one we're going to look at is some power of a sine times some power of cosine. How can we find an antiderivative to this function? As you can see, the book kind of lays out a recipe. If the power on the sine is odd, it kind of tells us what to do. If the power on the cosine is odd, it tells us what to do. And if they're both even, it tells us what to do. Now, the idea is there's going to be a lot of different kinds of functions and a lot of different kinds of recipes. So we want to, as much as we can, think about the strategy, because then if we know what the strategy is, that can help us know, which rules to apply. And there just ends up being less kind of things to just memorize. All right, so what if we're presented with a function like this? We can see that the power on the sine and the power on the cosine is odd, so we can simply just go to the recipe. But the whole idea here is we want to use u substitution at some point. And that's kind of the overriding overriding goal, is we want to use u substitution like where u is equal to sine or u is equal to cosine. Well, why is that good? Because if u is equal to sine, then du is equal to cosine dx. So that helps us get to a place where we can use substitution. In this case, we can see that sine is odd, so what we want to do is peel off all but one of the sines here. So we can write sine to the fifth power of x as sine to the fourth power of x times sine of x. Right, and then sine to the fourth power of x is just sine squared, and we want to use the Pythagorean identity here, that we want to change those to cosines because that's what everything else is in the integrand. So sine squared is 1 minus cosine squared. That's all squared times the sine of x. Good, so that lets us rewrite this integral then. So we have sine to the fifth, which we just found. So that's going to be 1 minus cosine squared x squared times the cosine to the ninth power of x times sine of x dx. Now, why is this good? Because now we can let u equal to cosine, and then du is equal to negative sine dx, so we have negative du is equal to sine of x dx. And now we can rewrite the whole integral using u substitution in terms of just u's. So we have a negative, okay, from the du, and then we have a 1 minus u squared times u to the ninth du. And that is a polynomial, right? We can expand that out and just get a polynomial function. So if we do that, just to finish it up here, we have 1 squared. So we have 1 minus 2 u squared plus u to the fourth, and that's all times u to the ninth. Right, and we can multiply that through. That's u to the ninth minus 2u to the 11th plus u to the 13th. Right, and then we can apply the power rule to each of those, and then put the u equals cosine back in. Right, so just for the sake of completeness, let's finish this here. So our antiderivative then in terms of u is we get a minus u to the 10th over 10 plus u to the 12th over 12 minus u to the 14 over 14 plus some constant of integration, and then we can just put our cosine back in. Negative cosine to the 10th over 10 plus cosine to the 12th over 6 minus cosine to the 14th over 14 plus some constant integration. Okay, so in a nutshell, that is how we can do problems where you have a power of a sine times a power of a cosine. Now, the next ones we're looking at are ones like this, where we have some a sine of some factor times x times the cosine of some factor times x. Essentially, we're looking at integrals that use this trigonometric identity. Okay, and so if you look at your trig tables, these are the sum and difference formulas, sometimes called in trigonometry. But anytime you're integrating a formula like that, you can just replace it with these trig identities, and those are easy antiderivatives to take, right? Because the antiderivative of cosine is sine, but then you divide by that factor in front because that's what you would have from the chain rule. Okay, so those are relatively easy to do. So what would you set up something like this? You would have the integral, well, we have a sine of 5 times a cosine of 2x. So it's a sine cosine situation, so that puts you in this category. So we just replace it, right? We replace it with the sine of the difference. So we have the sine of 3x plus the sine of the sum. So the sine of 7x dx. Okay, and then this ends up being a relatively simple integral. We have the negative cosine of 3x, right, all over 3. And we have a 1/2 times all of this stuff. And then we have a minus cosine of 7x all over 7 plus c. Okay, now the last part of these trigonometric functions that we're looking at are powers of tangent times powers of secant. And we have some things we know about the derivative and some trig identities that we can apply. And this is very much like the first case where we have some recipes. So let's do an example and see which situation that we are in. So I found a few of them here. And let's do number 19. Okay, in number 19, we want to find the integral of tan squared times secant to the 4th. Okay, so what is the whole idea here? The whole idea, very much like in the first case, is we want to use substitution eventually. And we want to be able to use the fact that the derivative of tangent is secant squared. So that lets us, kind of the du will swallow up a secant squared dx. So we can trade out 2 of the secant squareds, okay? This is the formula that we can use right here, right? That relates tangent squared and a secant squared. So how can we trade out to the secant squareds? Well, the recipe kind of tells us what to do. So let's just go take a look. It says if n is even, n is the power of secant, which it is, then what we can do is replace an even number of the secant squareds, all but 2 of them, with 1 plus tan squared. So that's what we'll do. So we have the tan squared that's already there. And we have secant squared x and then secant squared x. So we're peeling off like a secant squared x. And then this one we'll leave alone. But the other secant squared x we can replace as 1 plus tangent x. Tangent squared plus 1, I mean. Secant squared x dx. Now why is that good? Because now if we were to let u equal to tangent of x, and we can see that's going to replace most of that interval of x's with u's, then du is equal to secant squared dx. And now let's replace everything in here with a u. So we have a u squared times a u squared plus 1 du. And that is a fairly easy integral to find, happily. So we have a u to the 4th, so we get a u to the 5th over 5 plus u squared, so we get plus a u to the 3rd over 3 plus c, and we can put in our u back. So we have a tangent to the 5th power over 5 plus a tangent to the 3rd power over 3 plus some constant of integration.